Good afternoon, and maybe someone of you still has the microphone on because I have a bit of echo. I'm Alvise, as Jesper already introduced me. Today I will talk about Micro-FTIR chemical mapping or imaging. But before doing that, I just say a few words about me. I am from Italy. I studied chemical science in Venice, and I worked for some years for the National Research Council in Italy. And then I moved in 2016 in Aalborg, where I did my PhD, postdoc, and now I also work together with Jesper at the Build department, where I work mainly on microplastic pollution, marine pollution, and other type of environmental related pollution. My background is in analytical chemistry, but I also do something related to environmental engineering. So for today, the agenda is consisting in two parts. The first part will focus on a bit of a FTIR theory, how an FTIR work, a few definition, and then we will move from macro FTIR to micro FTIR, a bit of concepts related to micro FTIR microscopy, and then we will introduce what is micro FTIR chemical mapping. Then we will have a 5 minutes break, and then in the second part I will go more in detail talking about what is chemical mapping, its main application, and maybe a link or a potential link between the use of this technique and some urban drainage related topic that in my opinion could be a link can be found in the analysis of this emerging pollutant called microplastic in urban waters. At the end there will be a session of question and answer, and I hope I will be able to answer your question, so be kind with me, and I'll try also to be as gentle as possible, because somehow there is a bit of theory also to go through. So first part, so FTIR theory, spectrometer, few definition from macro to micro, and micro FTIR microscopy. So I guess most of you are familiar with the electromagnetic spectrum, which is basically comprising all the electromagnetic waves from the more energetic ones like gamma rays, moving to X-rays, ultraviolet rays, a very narrow region which include the visible radiation, moving to infrared waves, microwaves, to radar, radio, and television waves. The region that is just after, let's say, the visible region, it's called infrared region, and for convenience is divided in near infrared, mid infrared, and far infrared. The most commonly used region or part of the infrared region is the mid IR, and it's where the FTIR technique works. Let me change to laser pointer, that maybe is more useful. So why can we use infrared light for some chemical identification? If the infrared light is irradiating a sample, and a sample is made of molecules, this can be also, this radiation can be absorbed, and it can cause an excitation of the sample molecular vibration. If the energy of this incident light is matching the vibrational frequencies of the molecule, and there is a change in the molecular electric dipole moment of the molecule, this excitation cause the amplitude of the chemical bonds to change and cause also some active molecular vibration. But how these molecules are vibrating? They can basically stretch in a symmetrical or asymmetrical way, or they can bend. They can do it like together, alternating, and they can do it in plane or out of the plane of the molecules. This vibration, they happen at specific wavelengths for specific chemical bonds, and they can be recorded, okay? So this way, we can identify molecules and many other materials. In this specific case, the recorded vibration for these specific bonds, they tell us that this molecule is water. It's important to remember that molecules with no dipole moment change, they don't absorb in IR energy, like for example, oxygen or nitrogen. The absorbent position of this specific chemical bonds, they are listed in well-known tables. They can be found in books and online, and they are still used to do some so-called spectral interpretation. The so-called hardcore spectroscopists still do that. It's a bit old and tough way, and nowadays, luckily, there are also some spectral database that can be used to identify molecules through FTIR spectroscopy. So to summarize, there are some IR active bonds that produce some peaks. Every different type of chemical bond that absorb infrared light vibrates at specific frequency. And this small variation in the molecular structure can cause a change in the peak position and intensity. So we can differentiate and identify different molecules. So basically the infrared spectrum, which is this like a red line on the chart, is somehow a fingerprint of every molecule. In this case, it's a molecule of polyethylene, a very common polymer or plastic. But how do we measure this vibration? Let's introduce what are the instruments that are used for FTIR spectroscopy. So the spectrometers. The first one was commercialized in 1953, but the early IR spectrometers, they were very complicated and they had a lot of movable parts. Plus, they were collecting information on different wavelengths one by one, by moving a grating or a sector, and this was very time consuming, and it also was leading to a very low spectral resolution. Thanks to the studies of Jean-Baptiste Fourier and its Fourier transform, which decompose function of time, so a signal, into the frequencies that make it up, it was possible to optimize new systems. And in 1969, DigiLab invented the so-called FTIR spectrometer, so the Fourier transform infrared spectrometer. In this setup, we have only one part that is moving in the instrument, so only one movable mirror. We have a higher intensity of the source. It is a faster way of doing this type of analysis. We obtain a higher resolution, and the wavelength, the width of the wavelength, so the range is limited only by the source. So how does an FTIR spectrometer works? Basically, we have an infrared source located in a special place of the instrument, which emit an IR beam. And then this beam, through some mirrors, enters what is the core of the instrument, that is called Michelson interferometer. In this interferometer, there is a semi-transparent mirror called beam splitter. It can be done or constructed in different materials. And this beam splitter separates the incident light in two beams of equal intensity. One beam goes to a stationary mirror and another beam to a movable mirror. These two mirrors that are hitting these two beams that are hitting in two mirrors are then reflected and sent back toward the beam splitter. There is a wave recombination which creates an interference pattern. The recombined signal is then sent out of the interferometer and through other mirrors is sent to the sample, which luckily will partially absorb also some infrared light, and then the exiting radiation is collected by the detector. So what we record is a sort of interferogram, because I mean we have an interference pattern that we measure and we can record by an interferogram. By applying the Fourier transform, we can basically decompose the signal into the frequencies that are making it up. And then by doing another operation called background subtraction, we can finally obtain the FTIR spectrum of the sample we are analyzing. We can introduce some short, let's say, definition. So what is called a scan, or scans in FTIR are a complete movement of this interferometer movable mirror. The number of scans affect the signal to noise ratio. So if we want to obtain a better signal to noise, we need to move the mirror more times. So co-add more scans. We can do it at different speeds. So the speed of the mirror movement is also an important parameter called scan speed. And we can collect infrared spectra in different spectral range. So the scan range is the spectral range selected for the analysis. The most useful is from 4,000 to 400 reciprocal centimeters or centimeters minus 1. These centimeters minus 1 are the so-called wave numbers, which is basically 1 over the lambda, and they are exactly expressed in centimeters minus 1. We can express our infrared spectra as the ratio between the transmitted light through the sample over the incident light. In this case, we call it transmittance, or by applying the minus logarithm in base 10 of this ratio, we obtain the spectrum in absorbance. Basically, on a practical side, when we measure in percentage transmittance, our peaks are coming from top, and when we are measuring in absorbance, they actually grow from the bottom of the spectrum. How do we identify our spectra in FTIR spectrometry? Originally and traditionally, what we had to do back in the days, and I also did it, was to record the absorption band. They can be printed on millimetered paper, and then we can use the available table, like the one I showed you in one of the previous slides, to identify specific vibration of the chemical bonds. And then what we have to do is to try to draw the molecular or chemical structure of the molecule. It's a bit the old school chemical identification. And in this case, after probably 40 minutes of thinking and drawing, I concluded that this was a molecule of polyester. Luckily, nowadays, we have databases and we can do a library search. So basically, our red spectrum, which is the spectrum of an unknown sample, can be basically compared to many spectra in our databases. And then by also an evaluation of the best possible match, we can identify the unknown spectrum. In this case, a spectrum of polypropylene, which is another very common plastic with a very high degree of confidence, around 98% of matching. Why is FTIR spectroscopy so popular and widely used in analytical chemistry labs? Because it's simple to perform. It requires very little to no sample preparation. The results can be obtained within seconds to a minute, more or less. It's really powerful tool for analyzing gases, liquid and solid sample. It is versatile because it can accommodate various sample sizes and type, and it provides both qualitative and quantitative results. Also, it's quite accurate, and it can also be non-destructive, so it can be interesting, for example, in forensic science, where we have to be careful to destroy the samples because there are evidences. And also it's somehow an affordable method compared to other analytical techniques. When we work in FTIR spectroscopy, we can collect the sample, the signal from different samples in different ways or different sampling modes. The most traditional one, it's called transmission, where the infrared beam is sent through the sample and it is collected at the exit, let's say, after interacting with the sample. It can be used with liquid, gases, powders, and film, but it is a thickness-dependent technique. So a too thick sample will not be able to be analyzed via transmission. We can also perform FTIR analysis by collecting our signal in reflection. Either we use the diffuse component if we have a rough surface, so we do it mainly with powders, or we can work with the specular component from a sample. And in this case, we can analyze liquids, thin films, and also shiny bulk materials. So, for example, it's good for coatings like varnishes and paintings. The third way is called Attenuated Total Reflection, or ATR. And in this case, our sample, the green area, is placed onto a specific material called ATR crystal, and it's like squeezed by a clamp. The infrared beam from the instrument is sent through this special crystal, which is made typically of some high refractive materials such as germanium or diamond or zinc selenide. And then a part of infrared beam is extruding the crystal and entering the sample and then bounced back to the detector. In this way, we perform a so-called surface analysis, which is not dependent at all on thickness. So we can analyze also bulk materials that are not transmissive in infrared. And nowadays, I would say is the most commonly used sampling mode in most of the analytical labs. So today we want to talk about FTIR imaging. So from the macro sampling or macro FTIR, we have to move to the micro FTIR, so the infrared microscopy. What is an infrared microscope? It is a microscope that uses infrared light as a light source. And instead of using lenses, so refractive elements, it uses reflective elements in its optics, so mirrors. And it used these mirrors to magnify and focus the sample. The purposes of a micro FTIR are to allow the user to see small or micronized size samples and to obtain accurate infrared spectra of those samples that we just imaged with our micro FTIR. Infrared microspectroscopy can be done or performed in 4 ways: transmittance, like before; reflectance, like I just mentioned; again, the ATR or attenuated total reflection; and there is a 4th mode called grazing angle, but we won't talk about it in this seminar. An infrared microscope is basically an accessory that is connected to the spectrometer, okay? Like an ATR is, like other accessories. It is important to remember that the microscope is somehow throughput limited. So basically it doesn't have all the energy that the spectrometer has, because of course there is a longer path to reach the sample. And we are talking about the 75% of the initial beam energy. When we do microscopy, mapping, and also imaging, we need performance. So we need a very good spectrometer, which is this part of the instrument in a modern instrument, to have a better signal when we do infrared microscopy. Some common terminology related to infrared microscopy. We have to introduce the concept of magnification, so the ability of a microscope to produce an image of an object at a scale that is larger than the actual size, and basically allowing us to see more detail of this object in the image than when we observe it with our naked eye. Also, we have to introduce the concept of a field of view, which is the maximum area visible when we are looking through the microscope eyepiece or a scientific camera connected to the microscope. And remembering also that the field of view decreases when we increase the magnification, as you can see in this very simple representation. When we work with infrared microscopes, as I mentioned, we don't have refractive lenses, so like the lenses we have in an optical microscope. We have a different type of objective that is called cassegrain. It's somehow a terminology common also to people that are working in astronomy, because there are some telescopes that have a cassegrain, let's say, configuration. It's basically designed by using mirror instead of lenses to reflect the infrared radiation and focus it onto the sample and also through the sample. Basically, it's our way to then collect and send our infrared radiation to the detector for the identification. The infrared cassegrain is composed by parabolic mirrors, one on this side and one that looks the other way, and the infrared beam is basically bounced and focused onto the sample irradiating the sample and then collected back into the cascgrain when we work in a reflection. When we are instead sending our infrared beam through the sample because it's transparent to the infrared light, there is another infrared objective put upside down that is called condenser, and the condenser is basically refocusing the infrared beam exiting through this from the sample again, so that it can be collected and sent to the detector. The detectors are basically semiconductors that are sensitive to the infrared light, and they can be in microscopy composed by a single mercury cadmium telluride detector, a line of detectors, or a focal plane of detectors. And this is important because they are the second and the third type of detector are widely used when we do chemical mapping. Other concepts related to microscopy are the numerical aperture, which basically is the measure of the objective ability to gather the light. The higher the numerical aperture of an objective, the better is the resolution of the objective itself. But also, when the numerical aperture increases, the working distance decreases. Working distance is basically the distance from the objective to the sample. As you can see, when we move to higher magnification, the working distance decreases. So the objective is much closer to the sample. If we have an objective that allows us that it has like a very good or long working distance, we are more tolerant to changes in the sample surface topography, and we don't need to constantly refocus as we move around the sample. So we briefly introduced the detectors. Let's then quickly go through how we can collect a signal with a µFTIR. The most simple setup is the one with only one detector, and it can allow us to do a single point measurement where we collect one or more spectra of different area of the sample, and every point we collect is basically one infrared spectrum. And the aperture of the spot we analyzed is basically limited by four blades that are closing around a specific area of the sample. And it's also limited by diffraction around 20 square micrometers. When we have only one detector, we can also do some sort of mapping. So basically, we will collect several spectra moving on a grid automatically if we have a motorized stage. So the spectra are acquired one by one. It allows us to do small mapping around small areas of the sample, but each measurement point takes around roughly 1 minute. So it's a very time-consuming analysis when we have to map larger areas. So it takes many hours to days. So the solution to speed up the process when we want to do some chemical mapping is by using a linear array mapping. So instead of having only one detector, we have a line of detector. This is typically 1/16 detector or 2/8 detectors. And basically, in this way, we can speed up the process of mapping and obtaining basically both spectral and spatial information about our sample. But we are still a bit slow. So the best solution is when we have, instead of a line of detector, we have a focal plane array of detector, basically a square made of detectors, which can collect up to several thousands of infrared spectra simultaneously in a single measurement. This allows us for a faster mapping, and also we have a better pixel size that we will briefly introduce when we will go into the details of Ftir imaging or mapping. So basically, this so-called focal plane array imaging is the best way to do fast mapping and high resolution mapping. So with that, I concluded the first part of this small seminar. So if Jesper and the other agree, we could have a 5-minute break.